Hey everybody, welcome to Chapter 6, Section 6, Inverses of Functions. This is part 1 of a two-part series. Here we're going to talk about um, converting a function into the inverse of that function. And then we're going to be, plugging in numbers into that inverse function and identifying the domain and range of the inverse function. And then we'll do a little bit of graphing as well. Okay, so number 1 says let f of x be 2x plus 3. Find the inverse, where f is raised to the negative 1 power. So this and this is function notation. So this is inverse notation for function notation. Anything raised to the negative 1 power is the inverse of that. So if I were to just write like a 2, the inverse of that would be 2 to the negative 1 power, which is 1 over 2. So inverse is just flipping things, okay? If you want to think of it like that, all right? So the first thing we need to do here is just switch the x and y variables and then solve for y again. So f of x is interchangeable for y. And so it'll say x equals 2y plus 3. At this point, we're just going to solve for y, so I'm going to minus 3 to the other side. If x minus 3 equals 2y, so now I'm going to divide by 2. So x over 2 I'm going to write as 1/2 x minus 3 over 2 equals y. Alright, so for function notation, as I was saying before, you're not going to have it as y equals, you'll have it as f to the negative 1 power of x equals, and then it's the same thing, 1/2 x minus 3 over 2. So this is the inverse of 2x plus 3. Alright, so at this point, it's saying find the input when the output is negative 7, because normally you find the output when given an input, but since this is inverse, it's backwards. So it's like this is the output in the original function, and you'd be solving for x. But here, we're just going to plug in negative 7 into the inverse, and then we'll get our answer. So it's worded kind of confusing, but the math itself is really simple, okay? So we're just plugging in negative 7 for x. Even though it says y, it would be for y in the original. So it's going to equal negative 1/2 times negative 7 minus 3 over 2. Alright, so negative 1/2 times negative 7 is negative 7/2 minus 3 over 2. That would make negative 10 over 2. And negative 10 over 2 is negative 5. Alright, so what that is saying is, if you look at the table for 2x plus 3, you will, in fact, when you scroll to where x is negative 5, you should see negative 7 being the y value. In fact, here is the table of the original, and you can see when x is negative 5, y equals negative 7. So maybe it makes more sense now. See how it says y equals negative 7. But when you do the inverse, you plug it in for the x variable. Okay? At this point, I would like to identify the domain and the range of the original. So here the domain and the range of the original and the new one, excuse me. For the domain, it's going to be all real numbers, and the range is going to be all real numbers. And so when you do the new ones, you would just flip them. What you have on the range, you write for the domain, and what you have on the domain, you write on the range. Well, these are the exact same answers. Now, how do I know that these were all real numbers? Well, first of all, what were we dealing with? We were dealing with a linear function. And then what was my inverse? Also a linear function. So they're both all real numbers because linear functions are unbounded. And let's look at the graph to show you what I'm talking about. Here's the graph of both. You can see that it's moving up and down, left and right freely on the original and the inverse. That's how I know it's all real numbers. Maybe I should have started with looking at the graph, but so sorry about that if I confuse you for the moment. But hopefully it makes sense now. So number 2, let f of x be x squared. Find the inverse, and then we're going to do the plug in 25. So like I said, switch the x and the y, so it's going to say x equals y squared. So to get rid of a square, you square root. And so it's now going to say y equals the square root of x. But don't forget, anytime you do a square root, you can have a plus or minus answer. So I'm going to write plus or minus square root. So if I'm going to put that in function notation, I'm going to write it as two functions, and I'll tell you why in just a second. But I'm going to write f to the negative power of negative 1 of x. And then I'm going to write equals just a positive square root of x, and then equals a negative square root of x. I won't put the negative on the inside, only on the outside. And so I can answer the question as to why by looking at the graph now rather than at the end. So let's do that. Let's look at the graph now. So here's the graph. You can see that when you graph just the square root of x, you can't type in a plus or minus into a graphing calculator, unfortunately. So when you type in the square root of x, it just gives you this top curve. But remember, square root gives you a plus or minus, so you have to type in the negative side. And so when you do that, then it completes the parabola. And so you see the inverse of a parabola is just a sideways parabola, okay? So that's why I split it up into two sections, two functions. And so here I said find the inputs, and then I purposely bolded the S because you're going to have more than one answer when the output is 25. So, just think of it like this. What is the square root of 25? And remember, that's anytime we take the square root, we say plus or minus. In this case, 5. So I get positive 5 and negative 5. So those are my two answers. That's why I have inputs, okay? So let's talk about the domain and range. All right? So the domain of the original is all real numbers. How do I know that? Well, it's moving left and right freely. It's going to go left forever and right forever as it goes up. What is the range of a parabola? Well, this one starts at 0 and it's going up. It can't go to the negatives. So I'm just going to simply say y is greater than or equal to 0. So this is what I mean. You're going to flip your answers. Your domain is now going to be x is greater than or equal to 0. You're not going to write y is greater than on the domain. Your domain and range always have x and y. And my range is now going to be all real numbers. See how I put this answer up there, put this answer down there. You're flipping your domain and range. Why does that happen? Well, look at the graph. Now it's going sideways. So it's starting at 0 and it's going to the right. So going to the right is with the x value. So that would be x is greater than or equal to 0. And then, yeah, it's slowly going up and slowly going down forever. So that is all the real numbers on the y's, okay? So that's pretty much everything there is to say about number 2. Okay, so here I have 3x to the third minus 2, so I switch the x and the y. Now it says 3y minus to the third minus 2, so I'll add 2 to the other side. X plus 2 equals 3y to the third, so now I'll divide by 3. Oops, I forgot that. Okay. So divide everything by 3. And so you get y to the third equals, and I'll just keep this as a fraction. It's not a big deal. You can separate it like I did before, or you can keep it all together. But to get rid of the cube, you'll cube root, and cube roots don't need the plus or minus, so the answer is just the cube root of x plus 2 over 3. Okay, so at this point, we're plugging in 22. So let me write the answer in proper function notation, which is to the -1 power. Okay, so here I have the same thing I just wrote, but equal to f of -1 of x. So now I'm going to plug in 22. So what's 22 plus 2? That's 24. What's 24 divided by 3? That's 8. What's the cube root of 8? That's 2. So that's the answer when you plug in 22. Okay? Or if you plugged in 3 into this answer, you would have gotten, 2 into this answer, you would have gotten 22 out here. So the next thing to do is to identify the domain and range of the original and its inverse. So let's look at the graph. So here I have graphed the original and the new one. You can see that they're moving up, down, left, and right freely. It's going to happen pretty much for any odd exponent you have. So linear functions count as an odd exponent. That's power of 1. So power of 1, 3, 5, 7. You're pretty much always going to have an all real numbers situation for the domain and range. And so if you flip them, that's not going to change anything. You're still having all real numbers for your inverse functions. Okay? So on these next two, we're going to, I give you a function, we're going to graph the original, we'll put those points here and then graph them over there, and then we'll calculate the inverse and then graph some of the points there. And then we're going to talk about just a little bit the line y equals x. All inverses are reflection across that line, so it should look like it's reflecting across a diagonal line, okay, because y equals x is a diagonal line. So let's just get started with this first example, 3x minus 6, all right? So I need a few values to plug into my table. So type in, 3x minus 6 under your graphing calculator and hit Control T, or you could start at -6 on the y-axis and go up 3 over 1, up 3 over 1, and so on. But yeah, let me just plug in some table values real quick. So I started at -1 because the y value with that is -9, so if I went any farther back, I'd be going off the graph. So I'm going to plot these points over on my grid to the right, okay? Okay, so here I graphed everything, -1, -9, -6, 0, and so on. And I graphed a couple extra just to get a good line, okay? So now let's turn our attention into doing the inverse of 3x minus 6. So first thing I'm going to do is switch the variables. X equals 3y minus 6. So that means I have to add 6. And I will get x plus 6 equals 3y. And so now I'll divide everything by 3. And so x over 3 would just give me 1/3 x. And 6 over 3 would give me 2. And I can write that with f to the -1 of x equals that. Alright? And so all I need to do now is graph that. So here's the thing. How do I graph those points? Well, why don't you plug this in and press Control T and then look for these points in the table, and you'll see that those table values have actually flipped, okay? And we're going to put that here. Okay, so here I have 1/3 x plus 2, and those table values did in fact flip, so I'm going to graph those right now. Okay, so I graphed a few extra points, but I graphed it. Those are the lines. It doesn't really look like much right now, but go ahead and type in y equals x into your graph calculator if you need to. But y equals x is that perfectly diagonal line, so it's just going to go like up 1 over 1 through everything. So it's going to pass through all these little corners here. And so what it should look like is, well, like I said before, a reflection of that. So, um, you know, it does look like it is splitting my graph pretty good. It's like you have a little bit smaller of a gap here, so you have a little bit smaller gap there, and then you have a little bit larger gap here and here. So a kind of an eye test, so to speak, is that inverse graphs should look like a reflection across y equals x. How do you know for sure? You just take the coordinates and they should be in the reverse order. So if something's at like 2 comma 3, then it should be at 3 comma 2 on the other line. Or like over here, if something's at -1, -9, it'll be at -9, -1 on the inverse, okay? So that's all I wanted to say about the y equals x thing. So the last example here, we're going to do the inverse of x minus 2, and then this is important. X is going to be less than or equal to 0, and we'll talk more about that when we get there. But first, let's get some table values for x minus 2, but let's not use any negative x values, or any positive ones. Use only negative ones and 0. So I started at -4, and then I counted up to 0. And then I'll graph these points. I don't think I'll be able to graph this one. But I can't use any other values because I can't graph any positive values. So let's just take these and graph these to the best of our ability on the graph to the right. So it should look like a parabola just sliced down the middle because of that restriction of x being less than or equal to 0. So the next thing we're going to do is, look, just to kind of reiterate the point, I'm going to take these table values and just put them on the reverse column, reverse row, I should say, without even having to do the inverse, because that's what the inverse is supposed to be. So yeah, I just flipped them, okay? You can always double check your work by typing in your inverse and then typing in the original. The tables should look exactly the same, only in reverse order. So let's see what our function should be. You're going to write x equals y squared minus 2. And so you're going to have to add 2 to the other side. And x plus 2 equals y squared. And get rid of a square by square rooting. You have to do to the whole other side. So normally you'd say y equals the plus or minus of the square root of x plus 2. But because of this little qualifier here, you can't have a plus or minus. You can only have the negative, okay? So you're just going to write f of -1 will equal the negative square root of x plus 2. So that is our inverse function, just the negative side, again, because this is less than or equal to 0 up here. If it said greater than or equal to 0, this would be a positive in front. But yeah, so this is what I get when I plug it in. When I plug in the graph and pull up the table, you will get these table values. So let's graph those right now. Okay, so here in blue is the inverse, and in black is the line y equals x. So it does, to me, it does look like it is a clear reflection across y equals x. So this question I put on the notes, is it a reflection? Yes, it is. Why would it not be? But yeah, that's pretty much it. All I can say for these notes is just remember to flip things, okay? And stay tuned for part 2. Thanks for watching. Bye.